First of all, I'll show you a syllabus. Okay, this is your syllabus. Now you can see in module 1, what are in module 1 and module 2. We are mainly focusing on those two. Can you see this, Suraj?
Yes, ma'am, visible.
Okay, so you can see first module, open loop and closed loop systems, that we learned, classification we learned. Then the transfer function of LTI, linear time invariant systems, mainly mechanical, electromechanical systems, force voltage and force current analogy. I hope you remember we had dealt with that. Then block diagram reduction, representation and block diagram reduction also we dealt with. Then we went on to signal flow graph, what is Mason's gain formula applied to signal flow graph, and we discussed about characteristic equation. So that is module 1. Then when we passed on to module 2, we discussed about control system components, namely, which were the components that we discussed in the class? DC servo motors, DC servo motor, that is armature control mode as well as field control mode. Then we discussed about AC servo motors. In both these cases, or in all the 3 cases, we derived the transfer function. Then synchro, gyroscope, stepper motor, tacho generator are left to you as homework, not the homework, assignment 1. And some problems here was also given, that is electrical network was given as assignment, which you are supposed to submit on Monday, coming Monday. Then today we will be, and yesterday we discussed some details regarding time domain analysis. I said time domain analysis can be divided into 2, transient and steady state. Then we'll come to the later stages of transient analysis here, and the next module only you have the steady state analysis. Okay, so after completing this transient analysis, you will have a series test, and then you will have we will go to the 3rd module. Now, if I have time after completing module 2, if I happen to have time, I'll take a revision, just a revision class on 1st and 2nd module, which you may or may not attend. I may even keep it as an extra class. Even if one person is there to attend that, I will take a revision on all these portions, that is portion 1, module 1 and module 2. Now today we will be going to time domain analysis. Back to time domain analysis, I'll be considering only the transient analysis. Okay, I hope that is clear. So when we consider the transient analysis, the very first thing that we have to remember is what is the order of a, or you consider this as a first order system. What do you mean by first order system? First order. Okay. Now let us consider an RC, simple RC network. This is an R and C. You can draw along with me. This is a simple RC network. You have an input voltage EI. This is R, this is C, and this is I. Now, what are this is EI and this is E0, output voltage E0. Now, I am going to find out the transfer function of this simple RC network. Those of you who know how to derive it, kindly derive it, or else you can follow my own steps. When I write these steps, you can follow that and you can write. Okay, so if I write the first equation regarding this, how will I write? R into IT, this is IT, okay, RIT plus 1 by C integral IT dt is equal to EIT, equation number 1. Then I want to get the transfer function, which means I want to get this relationship E0S by EIS. Okay. So in this particular equation, equation number 1, E0 doesn't come. So I have to write one more equation. What is E0? E0 is a voltage across the capacitance. So I can write 1 by C integral IT dt is equal to E0 t. I am repeating the whole thing. I have already discussed about this. I am repeating the whole thing once again so that people who had not attended any of my previous classes can also understand. Now you know that when you want to find out the transfer function, you have to convert all these equations into its Laplace domain, into the Laplace domain. So I'll convert that and then taking Laplace transform on both sides. Taking Laplace transform on both sides. So you get RIS plus 1 by CS, because it is an integral, 1 by CS IS is equal to EIS. Equation number 3. Similarly, equation number 2, if I take Laplace transform, I get 1 by CS IS equal to E naught S. Now, in order to get the transfer function, I just have to divide one by the other. I get it as E naught S by EIS is equal to 1 by CS IS divided by R plus 1 by CS into IS. Now these two cancel away and I get the transfer function E naught S by EIS as 1 by CS divided by R plus 1 by CS, which I can manipulate or rearrange the terms, and I will get this as 1 by 1 plus RCS. You must be familiar with this, which I can write in general as 1 by 1 plus TS. I hope this is clear. Now, what is T called? Do you know what is the terminal or the terminology for T? What is T? T is equal to RC. Is called what? Anyone? You have already learned.
Time constant.
Time constant. Time constant. Correct. T is equal to RC is called the time constant. So, though I have taken, though in this case, I had taken a RC network, whatever be the system, it can be even a mechanical system having a mass and one damper only. Anyway, when you derive, you will get a similar kind of transfer function. So this transfer function is known as the transfer function of a first order system. Why first order system? Because the order of S in this case is S raised to 1. Order of the transfer function or order of the denominator. Now here, one more thing I want to tell you is here 1 plus TS is equal to 0 is a characteristic equation. I told you what is characteristic equation? The denominator of the overall transfer function equated to 0 is a characteristic equation. No, I can say that the order of the highest order of S in the characteristic equation is the order of the transfer function or order of the system, or the highest order of the S in the denominator is the order of the system. Because the order is S raised to 1 here, you call it as a first order system. Hope this is clear. I hope all of you have written down also. So now, or I'll take another slide. That's good. That's better, I think. Okay. So in that case, I can say for a first order system, the transfer function in general, instead of writing EIS, E naught S, I can write CS by RS. CS is the output, RS is the input, is 1 by TS plus 1. Or I can put that as a block as RS is the input, output is CS, and this is 1 by TS plus 1. This is the first order system. Okay. The next thing that I want to find out, now I am considering what I am asked to, no, today we are discussing about the transient response of a system. So next we are going to consider the time response of a first order system. Time response, by which I mean transient response. Transient response of a first order system. Okay. In which case, I am thinking about a unit, very important, unit step response. Okay. Now, all of you, to all of you, I just want to tell you this. In yesterday's class, we discussed about transient analysis as well as steady state analysis. When I mentioned about the difference between these two, I mentioned one important point, that is when you consider transient analysis is dependent on the poles of the system. It is dependent on the system and not on the type of the input. So when you do transient analysis, though there are number of standard inputs that we considered yesterday, namely impulse signal, step signal, ramp signal, parabolic signal, sinusoidal signal, etc. Though these were the standard signals that we considered yesterday, though there are a number of standard signals, when you do transient analysis, it is sufficient to do an analysis using only one signal, any one of the standard signals, because the nature of the output which we are interested in, the nature of the transient response, output you call, what is response? The output itself. The nature of the transient response depends entirely on the system, number of poles of the nature of the poles of the system, on the system, and not on the input type of input. So it is sufficient to do transient analysis on a system by using only one type of standard input. Usually we do it using unit step input. Okay. So unit step simply means that yesterday we considered this as T and this as FT, and I put this as A. If this A is equal to 1, that is, if the highest magnitude is 1, you call it as unit step, and then you call that as UT. Instead of FT, you call it as UT. That is the only difference, which means UT is equal to 1 and US will be equal to 1 by S if I take the Laplace transform. Any doubt till now? Yeah, I'll give you 1 second. Anyone, if you want to have any clarifications, you can ask. Is this much clear? I'm going to, this is the Laplace transform of the unit step. Okay. Now, I'm going to find out the unit step response. Now, I'm going to find out the unit step response of a first order system. So, what I'm going to find out is, you needn't rub anything that you have written on your notebooks. I'm just going to repeat it in another manner, which is one and the same as that what I have written. I just want you to know what it is. I'm going to derive the unit step response of a first order system. Okay. Which means, what is the transfer function of a first order system? Cs by Rs is equal to 1 by Ts plus 1. This is the general transfer function of any first order system, be it an electrical system or a mechanical system or an economic system or a financial system. This is the transfer function, where if it is an electrical system, you put T is equal to Rc or R by L, as the case may be. If it's a mechanical system, it depends on what all components were there in the mechanical system. Now, what do you mean by, all of you should be carefully listening, very attentive. What do you mean by response? Output. What is the input to the system? It's a unit step. So if I give a unit step as the input to the system, I want to find out what is Cs and thereby come to Ct. Convert back to the time domain. This Ct is known as the response of the system. I'll explain that once again. You have a first order system. If you are going to find out the unit step response, you are asking about the response of the system if unit step is given as the input. So input Rs will be Us. And you are checking for Cs and thereby Ct. Ct is the response. Cs is the actual response when you take in the Laplace domain. But when you speak about response, you are speaking in terms of Ct. So in this case, what is Rs? If I'm going to find out the unit step response, what is Rs? That is equal to Us, unit step iota. So it will be 1 by S. Is that much clear to all of you? Aditya?
Hello, ma'am.
Did you understand, Aditya, here? This, whatever I taught, do you require further explanation?
Ma'am, once more, എനിക്ക് നെറ്റ് സ്പീഡ് ആയിട്ടാ കേട്ട് ഭയങ്കര.
Okay, I'll go a little bit slow. Now, this is the first order system transfer function. Okay. And I have an input RS and I have an output CS. If I am asked to find out, the unit step response, it simply means that my input is unit step and I want to find out what is the response or how the system responds, or how I want to find out the output of the system. Or this should be, the input should be unit step, and I am going to find out what is CS, which is the response in the Laplace domain. But normally you find the response in CT, in time domain. You find out CS and then take the inverse Laplace transform and find CT. That is called as the unit step response. Is that now clear, Aditya?
Yes, ma'am.
Okay. Hope this is clear to everyone. Any doubt you can ask. I'm trying to go as slow as possible. If any doubt, you can tell me. I'll be stopping with this only, so I have enough time. Ask me if you have any more doubts. Anyone? Okay. So, okay. So I'm now proceeding. Okay. So CS by RS is equal to 1 by TS plus 1, where RS is equal to 1 by S because you have taken a unit step. Had it not been a unit step, it would have been, RS would have been A by S, any magnitude, say 5 by S. Which you will have 5 as the magnitude. So here I am taking only unit step. Okay. Okay. Now CS. Now CS will become equal to, CS is equal to RS into 1 by TS plus 1. That is equal to 1 by S into 1 by TS plus 1. Okay. Now, if I want to find out CT. So if I want to find out CT, it is not sufficient to make it remain as such. I should find out, if I want to find out the Laplace inverse, I have to take the partial fraction A by S plus B by TS plus 1. Can you find out the partial fraction and tell me? Please find out the partial fractions and tell me. Any one of you? Mohit Mohan undo?
Yes.
Mohit Mohan and Parvati and I, both of you just put in your effort and find out. Simple. Parvati and Mohit, try to find out. Once you find out, please tell me. Did anyone of you get? Not only Parvati or Mohit. Did anyone get it? Partial fraction?
So 1 by S minus T by
1 by
TS
S minus 1 by S minus T by TS
plus 1.
Yes, correct. So what will be CT? 1 by S, inverse Laplace of 1 by S is 1. minus what, and this I can write it as, this doesn't have a standard inverse, so I modify this as 1 by s by 1 by s plus 1 by t. Okay, s plus 1 by t. So what is the inverse Laplace transform of this? Anyone?
E raised to minus
E raised to
1 by t.
minus t by t. Correct, correct. This is your unit step response. Okay, this is your unit step response. And if all of you have written down that, just look into your notebooks, just listen to what I am telling you. Now, we started the class with derivation of the transfer function of a first order system. How did we derive that? We started the class by drawing an RC network. I think that is still there. Yeah, RC network. And in RC network, we wrote the equations in the time domain and then took the Laplace domain on both sides, and we found out E naught s by EIS, and then I got it as, rearranging the terms, I got it as 1 by 1 plus RCS. RC was taken as T, so that T is equal to RC was taken as a time constant, and we came up to the generalized form of transfer function for the first order system as Cs by Rs is equal to 1 by 1 plus Ts. And why is it called first order system? I said the order of S in the denominator, highest order of S in the denominator is 1. And so, or you can even say the characteristic equation, the roots of the highest order of the characteristic equation, highest order of S in the characteristic equation is 1. And so it's a first order system. So the next thing that we did was to write it in the general form as Cs by Rs is equal to 1 by Ts plus 1. Now, we were dealing with time domain analysis and mainly transient analysis. So the very first step that we can do is to give a unit step as the input to the system and check for how it behaves as in the transient domain. So how can you give a unit step? Instead of Rs, I give Rs is equal to 1 by S, and then Cs is equal to this Rs cross multiplying Rs into 1 by Ts plus 1, or 1 by S into 1 by S into 1 by Ts plus 1, which you get as by using partial fractions as this, and then you in order to take the Laplace inverse, you rearrange the terms and finally get Ct is equal to 1 minus e raised to minus t by t. This is the general unit step response of a first order system. Why is it called transient response? It is called transient response because Ct is a function of t. Whatever value of t you put on Ct, you will get whatever be the value of t, you will get a response. So if I provide a table, like if I can write a table with t and Ct, okay, t and Ct 0, say 0.1 seconds, 0.5, and then I calculate the value of Ct as Ct is equal to 1 minus e raised to minus t by t. I'll get a curve which you already know. You know, we had derived this for RC network. So if this is a unit step, I get this as 1. This is your input, RT. This is T. This is your RT. What will be the shape of? What is the shape of your CT curve? Anyone? Remember, it's an RC network. And where is the output taken? Output is taken across capacitance, or you are going to draw the voltage across the capacitance and how it builds up. You already know that it is in this shape, or else if you look at this equation also, you know that finally at t is equal to infinity, when t is equal to infinity, Ct is equal to 1. That is where it has reached. Is this clear? This curve is Ct. Anyone? Any doubt? Now substituting this, when t is equal to 0, you get 1 minus 1. When t is equal to 0, what is the value of Ct? 0. 1 minus 1, 0. When t is equal to infinity, what is the value of Ct? 1. 1 minus e raised to minus t by t. 1 minus e raised to minus infinity is 0. 1 minus 0, or you get 1. Here, Ct is equal to 1 minus e raised to minus 0. That is 1 minus 1 is 0. So, in between you have an exponential increase. Is so much clear to everyone? This is the first order unit step response of a first order system. Is so much clear to everyone? Whom should I ask? I don't know. Anyone can volunteer, tell me. Jinta, is this clear, Jinta?
Yes, ma'am.
Okay. Okay. Now, certain things I want to tell you in this case is, sorry. Something about time constant. Okay. 1. If there is some matters regarding time constant. What do you mean by time constant? In our case, it was RC because it was an RC network. What do you mean by time constant? Or what is time constant indicative of? If I have a large time constant, what do you mean by, what do you infer about the system? If you have a small time constant, what do you infer about the system? Anyone? Can you define time constant? Can you define time constant? Okay. Now, let me first find out the slope at the starting, or the initial slope of the curve. Initial slope. Slope is always found out by finding out d by dt of Ct at t is equal to 0. What is that? Just find out someone. Parvati, find out the slope d by dt of Ct at t is equal to 0. Parvati?
Yes, ma'am.
Yeah, on the what conduce d by dt of 1 minus e raised to minus t by t at t is equal to 0. What is that? D by dt of 1 and there is 0. D by dt of e raised to minus t by t minus e raised to etra varum 1 by t 1 by t e raised to minus t by t, isn't it? Now at t is equal to 0, it will become 1 by t, isn't it? You get a slope of 1 by t. So the initial slope is 1 by t. Or if I draw a curve like this, okay. It has started initially with some slope. I'm going to draw a initial slope. That initial slope is this value is 1 by t. That is y-axis 1 and the x-axis will be t. Is that so much clear to everyone? So can I define time constant as a time taken by the system response to reach the final value had it maintained its original slope of increase? All of you just write down and then I'll explain that once again. Time constant. 1. You can write this initial slope. Just write these equations, whatever I have derived. Please write these equations. And then draw this slope. So one definition of you can write, I'll just dictate this and you can write this down. Time constant can be defined as the time taken by the system response, to reach the final value, if it had maintained, that is what is meant. Had it maintained its original slope of increase. Had it maintained its original slope of increase. I hope that is clear. Now the system, all of you just listen. The system response was starting at this slope. And if it had maintained that slope, it would have reached a final value at this point. Which point? When the time t is equal to capital T. So capital T is the time taken by the system response to reach the final value. Had it maintained its original slope of response. Instead, it didn't maintain that. Instead, it went off exponentially. And within the time constant, it reached only this point. So within that time constant, it reached only this point. What is this value? Actually, where did it reach? Ct is equal to 1 minus e raised to minus, instead of t, t by t. At t is equal to t, Ct became what value only? Just calculate and tell me. E raised to minus 1. That happens to be 0.632, which you have already learned. So this value is 0.632, which means time constant can also be defined as the time taken by the system response to actually reach 63.2% of the final value. Write down. You can write this equation. Please write this equation and then I'll dictate. So in actual case, the system response reached only 63.2% of the final value. In actual case, the system response reached only 63.2% of the final value. Hence, time constant can also be defined as the time taken by the system to reach 63.2% of the final value. 63.2% of the final value. Third point to remember is time constant, or write down. Time constant is indicative of how fast the system responds to an input. How fast a system responds to an input. Last sentence. Larger the time constant, comma, sluggish is the system. Sluggish എന്ന് പറഞ്ഞാൽ it is slower is the system. Sluggish or slower is the system, comma, Smaller the time constant, faster the system will be. Smaller the time constant, faster the system will be. So that is all for today. I hope this portion is clear to you. It's very important. So I hope people who have an average time constant, people among you who have an average time constant has already understood. Some of you have very small time constant. You grasp it up just like that. Some of you may have a longer or a larger time constant to get these things done. They will be talented in some other things. But so you call some people tube lights, isn't it? Instead, you can always call them, you are having larger time constant. Hope this much is clear. Any doubt? I'm going to stop the class. Any doubts? Anyone? You can ask me. You can ask me. I don't have any hesitation to tell you. Amal K.A. Amal?
Yes, miss.
Any doubts, Amal?
No, miss.
Did you take down the notes? Now, these notes will be considered as an assignment and I'll tell you when. Okay. So, some of the notes you have to write. Okay. Amal, Amale? So, that's all. That's all for today. Tomorrow's the next class, we'll deal with second order system. So, I'll just summarize and then you can go. 1 minute, okay? What we discussed today was first order system. We took an RC network and derived the transfer function, and we saw the highest order of S in the transfer function was 1. S in the denominator of the transfer function was found to be 1, and so we call it as a first order system. So CS by RS, general format is CS by RS is 1 by TS plus 1, where that capital T indicates the time constant of the system. Then we went on to derive the transient response, or went on to derive the unit step response of a system, which means CS by RS is equal to 1 by TS plus 1. In that transfer function, RS was put as 1 by S. We cross multiplied, found the partial fraction, and we found out finally what is CS, and then we found out the inverse Laplace transform, what is CT. CT is equal to 1 minus e raised to minus small t by capital T. And if you plot CT, you will find that it is an exponentially increasing curve. And then we drew a slope for and then we found out the initial slope, and we found out that the initial slope gives you a very good definition for time constant. We said that if it maintained the initial slope, it would have reached final state at small t is equal to capital T, or time constant at a value of time constant. But instead, it reaches only 63.2%, or time constant is time taken by the system to actually reach 63.2%. And we said that the time constant is indicative of whether the system is slow or whether the system is fast. If the time constant is large, system will be slow. If the time constant is small, system will be very fast. So that is how a system is designed, thinking about the time. And in normal cases, we assume that the system has reached a steady state, final state, when t is equal to infinity. But in actual case, practical cases, we take 4 to 5 time constant as a time by which the system reaches a steady state. Thank you. That's all. I know I have gotten faster in the summarizing because I don't want you to lose your break time. Thank you so much. Thank you.